Imagine a medical scan. Cancer is present only if at least one cancerous cell exists. That's the core logic of multiple instance learning. A bag is positive if, and only if one of its instances is positive. But here's the problem. Most modern AI models for MIL don't actually follow this rule. They cheat. They use unconstrained layers that can learn invalid patterns, like defaulting to positive even when no real signal exists. This inflates performance, but fails in real-world settings. Our solution: a vector symbolic architecture, a mathematically rigorous way to encode symbolic logic in high-dimensional vectors. We represent each instance as a high-dimensional vector, nearly orthogonal to others. Then we use algebraic operations, binding, bundling, unbinding, to enforce the if constraint. A bag is positive only if one of its instances is a positive concept. To bridge raw data, like image patches, to this symbolic space, we train an autoencoder that forces representations to match VSA's core properties: zero mean, fixed absolute mean, and stable norm. Then we cluster these into a codebook, turning continuous vectors into discrete, interpretable concepts. The classifier: a MaxNetwork. For each concept vector, we compute similarity to all instances, take the max, then pick the minimum across concepts to prevent one dominant signal from overriding others. This ensures no cheating. On standard MIL benchmarks and medical imaging datasets like CAMELYON16 and TCGA, our VSA-MIL outperforms all valid MIL baselines, even beating some invalid models that cheat, while strictly obeying the MIL hypothesis. And here's the bonus: the concept vectors are interpretable. We can visualize which image patches activate each concept, revealing exactly what the model learned. This isn't just better performance. It's principled AI. A model that thinks like a doctor, not a trickster. VSA-MIL, where logic meets learning.